Today, we are tackling one of the biggest questions out there. Can we ever truly know what's going to happen next? I mean, really know it. Let's get right into it.
You know, for as long as we've existed, we've dreamed of predicting the future. It's kind of the whole point of science, right? To figure out the rules so we can see what's coming. But what if? What if some questions about the future are just fundamentally off limits? Not because we're not smart enough, but because the answers just can't be known.
So, to get our heads around this, our story has to start way back in 1814 with this incredibly powerful idea that really set the stage for how we thought about science for centuries. Okay, so check this out. A French scholar named Pierre-Simon Laplace came up with his thought experiment. Imagine a super-intelligent being, he called it a demon, that could know the exact position and speed of every single atom in the universe at one specific moment. If it knew that, Laplace argued, then the entire future would unfold for it like a movie it had already seen. The universe would just be one giant, perfect, predictable clockwork machine.
I mean, this was the ultimate scientific dream, right? A universe that's completely knowable, if only you could gather enough data. But this beautiful, orderly vision, well, it was about to get a serious reality check. And that reality check came in the 20th century, which threw a couple of massive wrenches into this clockwork dream. And they're probably ones you've heard about.
First up, you've got quantum mechanics. It tells us that down at the tiniest scales, things are just fuzzy. A particle doesn't have one exact spot for a demon to track. It's more like a cloud of possibilities. Then there's chaos theory, and this is the famous butterfly effect. It shows us that in a lot of systems, the tiniest, most microscopic error in what you know at the start can blow up over time, leading to a totally different future. Prediction just goes out the window.
But here's the kicker. What if you could get past those two problems? What if you could give Laplace's demon perfect, godlike knowledge with no quantum fuzziness and no tiny errors? Well, as physicist Toby Cubitt puts it, even then, you still can't predict everything. And this brings us to a third, much deeper limit on what we can know. It's this wild idea called undecidability. Think of it as chaos on steroids. It's not about not having enough information. It's the idea that for some systems, an answer about their future literally cannot be computed. The question itself is unanswerable. It's a limit that's baked right into the logic of the universe. So, where on earth did this come from?
Well, to understand that, we have to take a quick detour into the world of pure logic and the birth of computer science itself. So back in the 1930s, you have these brilliant minds like Kurt Gödel and Alan Turing, who are pushing the absolute limits of logic. Turing, in particular, asked what seemed like a simple question about computers. Is it possible to write one program that can look at any other program and tell you for sure if it will eventually finish its job, what he called halting, or if it will just get stuck in a loop and run forever? Okay, stick with me here, because the way he proved this is just beautiful. Step 1. Just pretend you could build that universal prediction machine. It looks at any code and tells you halts or runs forever. Easy enough? Step 2. Now, you write a new, kind of mischievous program called the contrary machine. All it does is take the predictor's output and do the exact opposite. If the predictor says a program will halt, this one runs forever. If it says it runs forever, this one halts. Now for step 3, the knockout punch. What happens if you ask the contrary machine to analyze its own code?
And boom, there it is. A complete paradox, a logical impossibility. If the machine predicts its own code will halt, its own rules force it to run forever. And if it predicts it will run forever, its rules force it to halt. It's a total contradiction.
And this led Turing to his staggering conclusion that universal prediction machine, it's impossible. Not because our technology isn't good enough, but because the very idea is a logical contradiction. The question of whether a program will halt is, in general, fundamentally unanswerable, or as he called it, undecidable.
Okay, so that's a really cool logic puzzle, right? But what's truly mind-blowing is that this abstract idea from computer science started popping up in the messy, real physical world. Scientists began designing these theoretical physical systems where this exact same undecidability would appear.
Take this, for example. Back in 1990, a physicist named Chris Moore imagined a sort of idealized pinball machine. The path the ball takes is like a computer running a program. And it turns out that asking the question, will the ball ever get out, or is it trapped forever, is exactly the same as Turing's halting problem. It's undecidable. And it gets weirder. More recently, physicists designed a theoretical quantum material on paper. They found that trying to calculate one of its most basic properties, something called its spectral gap, was mathematically the same as solving the halting problem. In other words, there are some fundamental things about this material you just can't know in advance. It's undecidable.
And maybe my favorite example, it even shows up in fluids. A mathematician, Eva Miranda, figured out that you could design a theoretical flow of liquid where the path of an object, like, say, a rubber duck, would perfectly mimic a Turing machine. So, asking if the duck will ever reach a certain spot is, you guessed it, undecidable.
So we've got pinball machines, quantum matter, even rubber ducks, all bumping up against this fundamental wall of knowing. But here's the million-dollar question. Does any of this abstract stuff actually matter for us, here in the real world?
Well, here's the big catch. All of these undecidable systems rely on some form of infinity. An infinitely precise starting position for the pinball, an infinite number of atoms, but in any real experiment we could ever do, everything is finite. So some people argue that undecidability is just a weird quirk of our theories, not of actual physical reality.
You have researchers like David Wolpert who put it pretty bluntly. He says, these results are profound, for sure, but they ultimately have no implications for us finite humans living in a finite world.
But of course, that's not the whole story. Chris Moore, the pinball guy, argues that dismissing these ideas is kind of short-sighted. I mean, think about it. All of our best theories of physics, the ones that describe fluids and fields, they all rely on the concept of infinity to make sense of the finite world we actually see.
And this is really the mind-bending takeaway. Even if the universe runs on a perfect, deterministic set of laws, those laws don't guarantee us any shortcuts to the answers. The universe itself might be the only and the fastest computer there is for figuring out its own future. Sometimes the only way to know what happens is to just wait and see.
And that leaves us with this incredible thought to chew on. The universe is going to keep on doing its thing, following its laws perfectly. But what does it mean for us, the storytellers trying to figure it all out, if we can prove with mathematical certainty that we can never, ever read the full story ahead of time?